Okay. Well, Friday at 5 o'clock. You guys are great. No, I thought no one's gonna come Friday at 5. The person who requested it can't make it. So anyway, how are you doing? Got a lot of studying to do for all your classes?
Yeah, definitely.
When's the bio final exam? Do you have an exam in bio?
Yeah, it's Thursday, I believe.
So it's pretty spaced out.
Mine's Wednesday.
Wednesday. All right. Well, what do you think? You want to start with some questions or what?
Can we start with 13 and 14?
Sure. I hope this catches up. Man. What the heck? Well, that's not going to work. I don't know. This internet is not cooperating, really. It's not catching up. Okay, let's see. Oh, I went too far. 13. Okay. Okay, about whether particular salts are acidic or basic or neutral. Okay, so LiClO. So what's the first thing you have to do when you're given a salt? What do you have to do first? You have to look at what?
If the first part is in like group 1 or 2, like if Li is in group 1 or 2.
Right, so you're looking at the ions, right? So we have lithium and ClO minus. Okay, so you already mentioned lithium. So lithium is in group 1. And it pairs in group 1, it pairs with lithium hydroxide. Any cation that it goes with a strong base is neutral. So that group 1 is neutral, group 2 is neutral. You could just say group 1 and group 2, it's neutral. What about the ClO minus? So what about this one? So you have to ask, sorry?
Basic?
Yes, that's basic. Why? It's the blank of a blank. It's the conjugate. What am I looking for here?
Conjugate base of a weak acid.
That's right. It's a conjugate base of a weak acid. And all conjugate bases of weak acids are basic. My camera is like crazy loose. Oh, that's better. Okay, so the weak acid is HClO. So if you could find the acid, the conjugate acid of this thing, which would be HClO, if you could find that in the weak acid chart, which it is, then you know that it is the conjugate base of a weak acid, and therefore it is basic. And since the other ion is neutral, it's basic. So it's B. Okay, so how do we do something similar for 14 here? So not, so here you have to identify the ions as well. And what are the ions? What's the cation?
NH4.
Not just NH4, it's NH4 plus. Okay, so it's important to include that charge in there. And the anion is Cl minus. Okay, so now what you're looking for are is the cation, let me write this down, is the cation the conjugate acid of a weak base and is the anion the conjugate base of a weak acid? Okay, so what about the first question?
You should remove a hydrogen from it.
You move at H plus. Okay,
Yeah.
So if you remove the H plus, you end up with NH3, which is a weak base. So the answer to that is yes. So that means that NH4 plus is acidic. Okay. So what about Cl minus? What is Cl minus the conjugate base of? What happens if you add an H plus to that? It's a long chorus of no answer. What?
It becomes HCl, a strong acid.
And the HCl is not a weak acid, it's a strong acid. And the stronger the acid, the weaker the conjugate base. So Cl minus is not basic. Conjugate bases of strong acids are neutral. So Cl minus is neutral. Okay. Do you get that? That's basically the idea.
Yeah.
If I gave you an example, like, let's go down here. If I asked you about this, for example, is this acidic, basic, or neutral? This is harder because trying to erase, won't let me. I'm stuck with it. Be NH4 NO2, not NH3 NO2. So here we have both of the ions matter. One of them is the conjugate. So NH4 plus is the conjugate acid of the weak base NH3. So it's acidic. And NO2 minus is the conjugate base of the weak acid HNO2. So it's basic. And we didn't really talk about how you would figure out if this is acidic or basic when you have one ion that's acidic and one ion that's basic. So it's harder to determine. We didn't go over that this year. I've done that in other years, but not this year in this class. What you would have to do is get the Ka of the NH4 plus from Kw over the Kb for NH3, and you'd have to compare that to the Kb of NO2 minus, which you would get from Kw and the Ka of HNO2, but we didn't do that this year. So just, it's harder to determine because one is acidic and one is basic, and that's all you can really say. So, what else?
Uh, 15.
Yeah, that's what I was thinking. We could do this one because it's a good problem. So I'm asking you for the pH of a salt solution. It'd be nice to first figure out if this is acidic or basic or neutral. So calcium, what's calcium? Acidic, basic, or neutral?
Basic.
Oh no, calcium is neutral. It's in the second group of the periodic table. So all those metal ions in groups 1 and 2 are all neutral. Okay. So it's really the fluoride here that's important. Okay. F minus is the conjugate base of HF. And so it's basic. So this is a basic salt. Okay. So what's the first thing you have to do if I tell you it's 0.136 molar of F minus, molar of CaF2? First, you have to figure out the molarity of the fluoride. So what does the fact that this is a 2 here do? What do you have to do to the molarity here to get the molarity of F minus? Come on, come on, come on, come on. What about the 2? What do I have to do?
Would you just like ignore?
Sorry, I didn't hear what you said. What?
No, never mind.
You have 2 moles of fluoride for every mole of CaF2. So you just have to multiply by 2 to get the initial concentration of the fluoride. So that's 0.272 molar of the fluoride. So that's just the beginning of the problem, though, because now you have to set up that hydrolysis reaction, F minus plus water. And what do I put on the right here? Blake, tell me. Come on.
HF.
HF plus OH minus, right? We have the reaction that H plus is going that way. So now I have to set up an ice chart here. The F minus is 0.272. This is a liquid, so we just don't care. 0 minus X plus X. Okay, so we have we have X squared over 0.27. Okay, now we need the KB for F minus. And you can't get that off of the chart directly, right? So F minus is basic, but it's not in the weak base chart. And just about all of the conjugate bases of weak gases will not be. So we need to figure out that KB for F minus is KW over KA for HF. And if you look up the KA for HF in the chart, it's 6.8 times 10 to the negative 4, and KW is 1.0 times 10 to the negative 14. So that KB of F minus is 1.5 times 10 to the minus 11th. So now we have to figure out, can we neglect X? And, you know, we can, because this is really small. 0.272 is way bigger than 100 times 1.5 times 10 to the minus 11th. When my pen comes back, I'll write that down. Because that's 1.5 times 10 to the minus 9. This is way bigger, so we can neglect the X. And so I'm running out of room here. X squared over 0.272 is 1.5 times 10 to the minus 11th. So X squared, just multiply out. Is 4 times 10 to the minus 12. So X is 2 times 10 to the negative 6. And now that's the hydroxide ion concentration. So when I take the negative log of that, that's the POH. And it's 5.70. So the pH, 14 minus that, and it comes out to 8.3, which is great because that's a basic pH. And we know this has to be basic, and it is, okay? So that's the pH. So in this type of problem, you know, you have to figure out what ion to react with water. Okay, I didn't go over how to do this for acidic salts. So it'll be a basic salt if I give you a salt, because we didn't do it in class, the other one. So you figure, you know, you have to take the ion, which is really going to be the conjugate base of some weak acid. So it's basic. React it with water. This is called a hydrolysis reaction. Gives you hydroxide. Do an ice chart. Figure out the KB for F minus, which is the K for this hydrolysis equation, and figure it out from KW and KA. Once you, and then generally you will be able to neglect the X in the, you know, unless it's really hard, which it won't be on a test. And then you take the negative log, get the POH, and then subtract from 14 to get the pH. A little involved, but doable. Okay. Squeeze that right into like a shoehorn. Right. What else? How are you doing with thermo? Shaking your head.
Oh, the next one.
This 16. This is what you want me to do?
Yeah.
That's right out of lab. Remember when you did the titration curve? Remember where it changes the most rapidly? That's the equivalence point. Is that what Dr. Lung called it?
Yeah.
Sometimes we call it the end point. So this is the equivalent point is where this pH changes the most rapidly. And that's at 40 milliliters added. So there's something called the half equivalence point, which is halfway to the end, to the equivalence point. And at the half equivalence point, the concentration of anion and the concentration of acid is the same. That's what it means, the half equivalence point. It's when you have half anion and half undissociated acid. And at that point, if we use the Henderson-Hasselbalch equation, if these two guys are equal, right, then this is the log of 1, which is 0. Anyway, so that term disappears and the pH is equal to the pKa. So if we go and find that the equivalence point is at 40 milliliters, then this is the half equivalence point right here at 20 milliliters. So 40 divided by 2 is 20. And if we look at what the pH is, I'm not expecting you to get this to a lot of significant figures. Looks like it's a little slightly under 5, maybe 4.8 or something. If you said 5, that's acceptable too. Okay, so that is the pKa. That's the negative log of the Ka. So if you look at the equation sheet, I have this equation, but I also have that 10 to the negative pKa is the Ka. So if you take 10 to the minus 4.8, that's the Ka. And that's 4.8. You have to make it negative before you do the inverse log. 1.5 times 10 to the negative 5th. Really, it should be just 2 times 10 to the negative 5th. It's just 1 sig fig. Because this only had one, because you only had 1 sig fig here.
Just quick question. Where did you end up getting 4.8 as a pH from?
Oh, because I went to the half equivalence point here at 20.
Okay.
And I looked at the pH at the half. This is the half equivalence point.
Gotcha. I see it now.
Yeah. And then that's how you get the pH, right?
Yeah.
From there. Yeah.
Okay.
It's really 1 sig fig because this is only 1 sig fig. You'd only end up with this 1 sig fig. Anyway, yeah. What's the answer to 12?
I just need to take a quick look at 14 again. Okay.
Okay.
So if it's the conjugate base of a strong acid, what does that make the anion again?
Neutral.
Neutral.
See, it says it up here. Because the stronger the acid, the weaker the conjugate base.
Gotcha.
So, the anions of strong acids are so weak that they're not basic.
Got it.
They're such weak bases that they're not bases. Yeah. Okay, what's next?
Can you go over 18?
18, sure. All right, so the pressure equilibrium constant, Kp. What would that be? Well, it's products over reactants, don't forget. It's pressures because I'm asking you for the Kp, so that's the pressure of N2O4 over the pressure of NO2 squared. Okay, so that's basically, that's A. And now you're given additional information that equilibrium happens when the pressure of N2O4 is 0.682 and the pressure of the NO2 is 0.318. So we could easily find that numerical value of that equilibrium constant by taking 0.682 over 0.318 squared. Then you get 6.74. Okay, so what does this favor here? Does it favor the reactants or the products?
Products?
How do you know that?
Because the Kp is large.
It's large. Basically, 1 is the cutoff, right? It's greater than 1. This is not overwhelmingly favoring the products. Like if the K was 58,000, that would really be favoring the products, but it's greater than 1. So you'd end up with more products than reactants at equilibrium. And indeed you have that, right? You have 0.682 to 0.318. So favors of products because it's greater than 1. Yes, so because it's large. It's not, like I said, hugely large, but it's not, it's greater than 1. So we're expecting for the sign, what do you expect the sign to be here? If the K is greater than 1.
Negative?
Sorry?
Negative?
Yes. Sign expected to be negative. So if we don't get a negative, then we did something wrong. So delta G0 is minus RT times the log of that K. I'm going to use R in kilojoule units, kilojoules per mole Kelvin. I love it when it writes it and then it erases it because it doesn't have the memory or whatever. I don't know. So this is minus 8.314. That's 10 to the negative third. Temperature, if you're not told, it's 298 times the log of 6.74. Now, because this is greater than 1, this log is going to be positive. That's how the answer is going to come out negative, because you have that negative sign in front. And you have to remember, this is a natural log, right? Don't go hitting the LOG button here. This is 1.908 times the 298 times the 8.314. The whole thing comes out to negative 4.72. Okay, kilojoules per mole. So it is negative. Good. And because K is greater than 1, but not hugely greater than 1, the K is negative, the delta G is negative, but it's not like negative 400, it's just negative 5, right? It's negative, a modest number. Okay, so what is the sign of the delta S? Should know that just by looking at this reaction.
Positive?
No, it's negative.
No. Oh.
Because here you have 2 moles of gas, right? Going to 1 mole of gas. You also have 2 less complicated molecules going to 1 more complicated one. So you have more disorder on the reactant side. That's negative. Okay, makes sense, Blake?
Yeah.
Right, okay. Okay, so we have our equation here, delta G is delta H minus T delta S. We have already figured out that we know that the delta G is negative. You know that the delta S is negative, so that this term here is positive. Okay, so can you answer this question now? It should start with, since delta G is negative, delta H must be negative, right? Because otherwise, how could delta G be negative? Because this term is positive, right? Okay, so delta H has to be negative, or else delta G couldn't be negative, right? Because negative T delta S is positive. So if delta H was positive, delta G would have to be positive. Are we okay on that? Okay. All right, so now we know that the delta H has to be negative. We just determined this. Okay, so now we have that we have 2 competing terms here in delta G. Okay, so the delta H term makes delta G negative, but the negative T delta S term makes the delta G positive. So here's the when we know this reaction has a negative delta G at 298 Kelvin. So here's the question. Given these signs, is the reaction always spontaneous? So what's the answer to that?
No.
No. Okay. When would the reaction not be spontaneous? When would the reaction when would the reaction be non-spontaneous?
At high temperatures, because then the term negative T delta S will be large and
Yes.
overpower delta H.
That's right. That's right. So the answer is at high temperatures. And for exactly the reason you said, because that would make the T delta S term large. Okay, so that's when the reaction is non-spontaneous, it's at high temperature. So no, it's not spontaneous at high temperature. It's spontaneous at low temperature. So with 298 Kelvin, is that a high temperature or a low temperature? Based on this conversation.
Low?
Right, because it's spontaneous. So since the reaction is spontaneous at low temperatures, and since it's spontaneous at 298, 298 is a low temperature for this reaction. And you'd have to have a temperature higher than that for it to be spontaneous. So does it actually ask? No, it doesn't. But let's calculate that crossover temperature. Oh, we didn't calculate delta S, so we can't. We'd have to know the value of delta S. So here in this problem, we don't know that value. So we can't calculate the crossover temperature without that information. So if we knew the delta S0 value, we could calculate the crossover temperature. I think actually I have another problem on this reaction somewhere. Oh, maybe we did it in class. I think we might have calculated that crossover temperature, but I think it was for the reverse reaction. So anyway, if we knew it, we could calculate this as delta H over delta S, but we don't know it, okay? All right. That's that. Well, what do you think? You want to do this one? You want to go with some other one?
That one is good.
This one?
Yep.
19. Go ahead. Calculate the delta S. Did you work on this already? I don't want to do all the problems for you, you know? Okay. Yeah, the delta H0 is easy because these two, it's 0. So you don't have to worry about that. Oh, what's the answer to this question here? Is this reaction, if I draw reactants and products, which is higher in energy and which is lower?
Is it 2?
Is what 2?
That the choose best answer.
Oh, is it 2? Number 2.
Yeah.
Yeah, it is 2. So this reactants are down here, products are up here. It's uphill. So you end up in a less stable okay, and so you have weaker, or you breaking more and or stronger bonds than you're forming. I know that because breaking bonds requires energy, and because you end up less stable, you must have broken more bonds than you formed. So yeah, it's 2, and that's how you know, because stupid pen. So you're absorbing more energy than is being released. And I know that because the reaction is uphill. So that's how I know. All right, so what do I have to do to answer C? What has to happen there? So what do we have here? We have delta G. It's delta H minus T delta S. Okay, so delta S is negative. Delta H is positive. So negative T delta S is also positive. So what's the answer to this question? What happens when you have 2 terms that are the same? So both of these terms are positive. And there's nothing that you could do to the temperature to make it negative. So you're never going to have a negative term here. Both terms are positive. The reaction is non-spontaneous at any temperature. So the answer is it's not spontaneous at any temperature. It's not spontaneous at 298. I don't even have to do any math, right? I don't have to actually calculate delta G to know that it's positive, because both of those terms are positive, although I do calculate it on the answers. But I don't really have to. It's going to be positive. It's actually 207 kilojoules. If you wanted to calculate it. Okay. Good.
I was going to ask if you could re-explain D, because I'm having a bit of trouble with 18D, I mean.
Oh, right. So remember when we talked about entropy, that, entropy is disorder. It's the ability to dissipate heat.
Yeah.
When you have gas molecules and you have more gas molecules, every molecule is moving. It's moving a lot, has thermal energy. It's spreading that energy around as they collide with each other. So the more moles of gas you have, the more disorder you have, the more heat dissipation you're going to have. If you have several smaller molecules that make up a big, more complex molecule, that complex molecule can't move around as independently as much as all those molecules that we use to make it up. It cannot disperse heat as easily as separated molecules. So 2 moles of gas going to 1 mole of gas, you've decreased the ability of that system to disperse heat. You've decreased the disorder. Another reason you could think of is that, you know, NO2 is less complex than N2O4. N2O4 cannot, does not have the disorder of 2 NO2s. It does not have the ability to dissipate heat as these less complex molecules. So, you know, the more.
So from this, so there's 2 moles of gas on the reactant side, 1 mole of gas on the product side. So
Yes.
there
That
is
alone
more.
tells you delta S is negative.
Okay. So there's more disorder on the reactant side than order on the.
There's more disorder on the reactant side than disorder on the product side. There's more order on the product side and less order on the reactant side. So you're increasing order, you're decreasing disorder. Entropy is like disorder. Think about it that way. You'll always be right.
Okay.
Mm-hmm.
2 moles again.
What?
So there's more disorder on the reactant side, is what you said, right?
Yes. Yes.
Okay.
Yes.
All right. Thank you.
You're welcome. Mm-hmm. What about this one, 20A? Is that true? What happened? Oh, well, it's not listening to me. It's one of those things. Well, that was really inconvenient. What happened there? See if I can fix it. I think I'm messing this up worse. Oh, well, I'll try to fix that later. I don't know what this was. But well. Ugh. All right, what's next? I think this actually is way further up. Hold on. I don't know. Okay, let's give that a rest. Mhm. Oh, God. Technical difficulties galore. It's not happening. This thing is so slow. Oh, well. Ah, I give up. I think I made it worse, but that's okay. Ugh. Mess. Look at this. Oh, well, that's all right. What's the next question?
Which one? 21B is kind of, the rest of it looks familiar. It's just B is asking like, what's the change in enthalpy for this reaction? And I'm kind of can't really recall anything about that.
Let's see. Okay. What do you mean? It's just using these data here, right? Enthalpy is a delta H.
Oh, okay.
Yeah. Actually, there's only one thing. These all have delta HF zeros of 0, but this is the
Okay,
only
that
thing.
actually, this learning that delta S means entropy and delta H means enthalpy, that helps me a lot more understand 18B now.
Oh, good.
Yeah.
Anyway, that's how you get 18B. I don't seem to have 18. Oh, here it is. Wait, no, 21, not 18. Oh, I'm sorry. So what's the change in entropy for this one then, given what we just talked about a while ago?
Give me a second.
Don't calculate it, just by looking at it.
Just by looking at it. Okay. So
You have 1 mole, you have 4 moles of gas here. You have 2 here.
So it's a negative change in entropy.
Yes. And then you
So
could
when we say
prove
negative,
that.
when I say negative change in entropy, what does the negative sign mean?
It means the okay, so it means that entropy is going down.
Oh, okay.
That's because the products have a lower entropy.
Yeah, the products are becoming more ordered.
Yes.
And entropy is disorder. Okay.
Products are less disordered and more ordered. Okay. And then you can actually calculate it. Delta S0 is 2 times this minus 3 times this minus 1 times the 191. And you can see that it comes out to negative 197, which indeed is negative. So it goes along with what we already knew, that it's negative. So we have a negative delta S. We have a negative delta H. Okay. So delta G is delta H minus T delta S. So it's negative 91.8 minus T times, now we just have to make this 0.197, okay? Because this is kilojoules and this is, we need to make it kilojoules per Kelvin. Here we have joules, so we have to divide by 1,000 before we multiply by the temperature.
Just quick question. Wouldn't it be 3 times, wouldn't it be a plus 1 times 191?
No, it's products minus reactants.
Products.
Over here?
Yeah, products minus the sum of reactants, right?
Right, but when you subtract the sum of the reactants, you have to subtract. So what I do is I subtract, I automatically distribute my negative sign.
Gotcha.
Instead of doing negative of this plus this plus this, I immediately write negative this minus this minus this.
Yeah.
Then I don't make a mistake.
Yeah, okay.
You know. Yeah. Okay, so now we have to figure out if the reaction is spontaneous. And when you see that, let's see. We have two competing terms here, it's true, because the delta S is negative, so this is positive. But the delta H is a larger magnitude, apparently. This 298. This is actually plus 58.7. So you could see this is more negative than the, God, I think it's crazy. This number here, 91.8, is more negative. This is positive. So it's negative. And so the answer is yes. It's spontaneous under standard conditions at 298. And this is just a little practice. It says using delta G F0s, verify that your value of delta G and C is correct. Because I could have used the delta G0 is 2 times the delta G F0 of ammonia minus 3 times the delta G F0 of H2 minus 1 times the delta G F0 of N2. But these are both equal to 0 because any of these formation deltas are 0 because you're forming an element from the element in its stable form. You're not doing anything to it. And this is the only number that's given because it's the only one that's needed. And 2 times negative 16.55 is negative 33.1. So it's the same. Okay.
Yeah.
Yeah. So now it asks you, what is Kp? So here you're using the delta G is minus RT log of K, but you're using it kind of in reverse. So e to the negative delta G0 over RT is K. Okay. You have to use R in kilojoules per mole Kelvin and 298. I'm just asking too much of this computer. Or maybe it's the internet, or maybe it's everything. I don't know. So this is the exponent. Actually, it's the negative of the exponent because this is the delta G. And I need minus delta G in the exponent. So be very careful about this. But you know the delta G is negative. So you know that the Kp has to be greater than 1. So if you get a Kp that's less than 1, you probably made a mistake with the sign of the exponent. Because this exponent is, so this is negative 13.4. So you need e to the negative 13.4, or e to the 13.4, which is 6.6 times 10 to the 5th. So that's, that's a pretty big K. That's greater than 1, right? So we must have done something right, because we got a K that's greater than 1, which is what we knew we had to get. Okay. So this question is the reaction spontaneous? Okay, so what do we know about the spontaneity of this reaction? We have delta G is delta H minus T delta S. Is this reaction spontaneous at all temperatures? Let's see what we have, We have a negative this, so that term is positive. This term is negative. Okay, so what's going to happen as the temperature goes up? The reaction is spontaneous here at 298. Will it always be spontaneous? What's the answer to that?
It won't always be spontaneous, but I'm currently just trying. Yeah, it won't always be spontaneous.
So when will it not be spontaneous? What would have to happen? At high temperature or low temperature?
Well, if you want to verify that, you can do like the absolute values thing, because they're competing terms.
Yeah, but I'm just asking you to just casually look at this and to tell me the reaction will not be spontaneous at what? Because right now we have a delta G that's negative because the delta H is the dominant term, right? And the delta H is negative.
So the reaction will not be spontaneous at high temperatures.
Right. So the reaction will become non-spontaneous. Because that T delta S term will start to play a bigger role. And so I think that I probably asked you what the crossover temperature is. Maybe not. Yeah, it's H. Well, let's figure it out, okay? So the crossover temperature is the delta H over the delta S. So minus 91.8 over minus 0.197, because go back and you could see, I can't see, it's not there. It disappeared. Oh my God, where is it? Oh, here it is, 197 for the delta S, so it's 0.197 negative. Okay, so do that 91.8 over 0.197 is 466 Kelvin. So what that tells you is that there's a change at 466 Kelvin. The reaction goes from being spontaneous to non-spontaneous. Okay. The delta G becomes positive at 466. If you remember where this comes from, right? It comes from setting the delta G equal to 0. Figuring out temperature does the delta G equal 0, because at some point between the reaction having a negative delta H at low temperatures, at some point the reaction goes from having a negative delta G at low temperatures to having a positive delta G at higher temperatures. And if delta G goes from negative to positive, it's got to go through 0. And that's the point that we use to calculate the crossover temperature. Okay. And so now if we actually calculate, let's see, I kind of ignored what it asked for here, which was find the delta G at 600 Kelvin. So let's do that, okay? You know, when I don't get a lot of response, I just keep going. So you're gonna have to stop me if I'm like going too fast or if I'm leaving you in the dust. What am I doing? I really don't know. I taught the whole year like this. I never knew what any student might. Every now and then I would stop and ask, and someone would say, "Oh yeah, you know." But
I think the pace is fine. It's
talking to the microphone.
I think the pace is fine. It's more that I think after this, I'm definitely gonna go back over it by myself.
Okay.
I'll probably take a nap.
So I think I said, let's calculate the delta G at 600. So the delta H, this is, by the way, assuming delta H and delta S don't change, which if you took PChem, you'd learn that they do change, but not by that much. So this was the delta H that we got. And now we want to put 600 Kelvin in here. And the delta S is, again, negative 0.197 kilojoules per Kelvin. This computer is getting so hot that it's hard for me to even touch my hand to it. Okay. So let's see, 600 times 0.197 is plus 118.2. So you could see that we are above that 466 Kelvin here at 600, and our delta G has become positive. So this reaction has become non-spontaneous. Okay. And now we can actually use this delta G0 to calculate the equilibrium constant. And just e to the negative delta G0 over RT. Well, I don't like doing it all at once. I like doing the exponent separately. So that's 5.29. So e to the minus delta G over RT. I have to put a negative sign in front of that. And that's 5 times 10 to the negative 3. So you could see that, you know, in changing the temperature had a huge effect on the equilibrium of this reaction. It went from being 6.6 times 10 to the 5th, really favoring the products at 298, to really favoring the reactants. And that's because the reaction has a negative delta S that we figured out up here. And at high temperatures, that negative delta S really makes the delta G positive. It makes the reaction non-spontaneous, and the K takes a nosedive. The equilibrium constant goes from being way greater than 1 to being way less than 1. So spontaneity changes a ton in this range. Let's see. No, pen won't write anymore. Great. So the reaction goes from being spontaneous, not spot. So what made it spontaneous was due to the negative delta H to being non-spontaneous, okay? So that's the answer. And this diagram here kind of summarizes it. If I put this diagram right here, kind of shows you as you go from low to high, crosses from being spon to non-spon. Okay. Yeah. All right. Any other burning questions?
No.
I don't think so.
Yeah, my computer can't take much more of this, so.
Could you go over Le Chatelier's principle in 7?
Sure, sure. Oh yeah, I know that question. So this is really asking about something about buffer solutions. So you know how you can always neglect X in the buffer solution problems? I don't ask you to justify it. The reason is if you have a weak acid, let's just call it HA. Well, actually, this problem is talking about acetic acid, so I could just do HOAC. No, I can't. It's not letting me. So assume this is acetate, OAC minus, and this is HOAC. Okay. And so if you have a 0.125 molar solution of HA, and you have the decided to erase it, and you have this equilibrium, okay, and then you add acetate to make the solution 0.15 molar in acetate. So just if you had this equilibrium without the acetate initially, and then you added the acetate, what would that do to the equilibrium? Which way would that drive the reaction? So if you have just HA and you set up the weak acid, because that's a weak acid equilibrium, then you add A minus, this drives the reaction in reverse. So it means that the concentration of H3O plus, when you have the added anion, the added acetate, is actually lower than if you didn't have that anion there. If you just had the weak acid equilibrium, this drives the reaction in reverse. And so H3O plus reacts away to some extent. So you actually have a lower concentration of H3O plus in a solution with a weak acid and its conjugate base than if you only had the weak acid. Sometimes this is called a common ion effect, where you add an ion that is common to the equilibrium and it drives the reaction the opposite way. Did you want me to calculate the pH here or just talk about the Le Chatelier's principle?
No, just the principle was the part I was confused about.
If you just looked at what the pH would be for 0.125 molar HA, you end up with X squared over 0.125 minus X, which we would neglect, equals 1.75 times 10 to the negative fifth. If you calculated X and you got a pH, well, let's see what it would be just for grins. 1.75 times 10 to the negative 6 times 0.125 square root, it would be 4.7 times 10 to the minus fourth. And if you take the negative log of that, that's a pH of 3.33. But now if you add this, you've driven the equilibrium in reverse and it'll be a higher pH because you have less H3O plus due to this reasoning here. And if you use the Henderson-Hasselbalch, you could probably figure this out pretty quickly. pH is P. Now that you said that I shouldn't do it, I did it anyway. So it'd be the negative log of 1.75 times 10 to the negative fifth plus the log of 0.150 over 0.125. So it comes out to 4.757, I think, minus 0.079. Yeah. No, it should be plus 0.079. 4.84. So, you know, it went from 3.33 to 4.84 by adding the acetate, driving the equilibrium in reverse. Did I answer your question?
Yeah, you did.
Okay.
Wouldn't the pH have more sig figs though?
Yeah, I just did it fast. You're absolutely right.
Okay.
Yeah, it would. Mm-mm. Okay, there you go. Right, okay. All right, I think that's good. I can't touch my screen anymore.
Thank you very much, Professor.
All right, I'll see you Sunday if you come back.
Oh, wait, there's a Sunday review session?
12 o'clock.
Yeah, it's yeah.
All right.
Yeah. All right.
Have a good one.
Bye.
Bye.
Professor, when will
Yeah.
you be posting the answers for the review?
I think that I had it timed. I think it might already be posted.
Oh, okay.
Wait, oh yeah, I'll check. Hold on a minute.
I think they are posted.
I think so. I think I had them post around sometime this afternoon.
All right. Thank you.
Yeah. If they're not, I'll make sure they are. I'm pretty sure they are. All right.
Yeah.
Bye-bye.
Bye.